This is the last of a series of 6. This is called my magnetic spinning wheel. I believe there's a spinning wheel that's always active, it's always spinning, and it's always dynamic. We'll go into the theory later on. I have a set of 20, a stack of Neos, 20 over here, facing north up, and on this side I have a magnet. There's 2 Neos north facing up. I have this set up for my power supply. That's just enough to either spin or spin for a little bit and then finally stop. You got to really work with that to get that just right. This is an isolated system. There is no interaction. This is another insulated also. There are no extra magnets being applied to make it stronger. There's no other motors to help give it power. There's no pulsing. It's just a DC, and you see what the power supply is. The motor is out of a VCR. It's a 12 volt. Okay, I'll go ahead and start it up again. Okay, go into what I think is going on. I may be completely wrong. It wouldn't be the first time, but that's okay. But I believe there is some type of flux, magnetic flux, that is spinning. We'll do a couple experiments that you can do. This one here is not quite works like the magnetic wheel, but it does show you that there is something of a stream of electronic flux that is going and active. This is a pack of 20 north face. This is a north face with a small boulder screw on it. Swivels easily. If you go down too low, then north and north they repel. On this side, unlike poles attract. But if you get out of this barrier, this wall that's close to the magnet, the forces are just so strong it builds up a barrier there, and that's basically what people have to contend with, and haven't found that higher up, if you lift this up high enough, there's a spinning magnetic force. So I'm going to come up a little bit from that so I get into that wheel more easily. See how it seems like it's riding up over the wheel? Seems like it catches. This diagram isn't quite right for what we're doing on this one. I said this isn't quite works with the wheel theory. But anyhow, it seems to ride up over the wheel, catches it, pulls it through, and then releases it pretty nicely. Okay. Another experiment. If you have I have a masonry nail, it's iron. Same pack of Neos. You get right into the center. That's that neutral zone. Forces are pretty much equal. There's no tendency to pull to the side. But if you get off a little bit, then very strong forces are there. In the center. This is very important, this neutral zone. You don't have that interaction. If you, instead of having an iron metal, if you have another magnet, this is north facing up, this is north facing up, take your magnet, come into the neutral zone. You don't really feel too much at all. When you come up a little bit, you just feel like a little bit of a zip there, and just flings it out. You don't want to get too close where it'll pull right in there. So you want to stay out just a little bit. Very strong forces careful with these neos. Okay, into the neutral zone, let it ride up, out, back into the neutral zone, up. If you come back the other way, the other direction, you really feel a lot of resistance there. Get back down into the neutral zone, that's neutral. If you go this way, you can feel quite a bit. You can do this in 30 seconds, so I'd advise you to do that. Okay, so what's happening here? Normally, let me get my other, I don't know if you'll be able to see this. This is off the internet, you can look that up too. But this is a magnet and iron filings. And you can kind of see there, it looks like a wheel. Well, actually, if you look into the bar, the metal, the magnet itself, you'll see straight lines coming through. So the wheel doesn't come through there, otherwise these lines would come through here like that. But they seem to be the wheel comes up and then follows the return path through the magnet itself, spinning this way. So you have a, let's say a counterclockwise spin here. There's another wheel down here that's going counterclockwise. They seem to be active, they're dynamic, and they are spinning according to my research. Okay, we'll just undo this again just to show you what's going on. I'd let your motor warm up for about 5 minutes or so to get it stabilized. Okay. Also, what are we doing? Taking 7.07 amp. Okay, so let's see if that changes any. .05, .06, .07. We're actually drawing less current, but we're having faster RPMs. That's what makes me think this is a dynamic, active spinning wheel. They do talk about static forces and angles that create reactions. Yes, that's true, but then they stop. They lock up. That's it. They react, and then that's it. But this one is not locking up. It seems to be continuous, continually recycling. So that gives me the only other way I could think of, you know, to have this be functional is to push it, give it some more power, perhaps have another little motor here, have a jet of air hitting it, something dynamic, active, pushing it. And also this is a separate here, and this is a separate here. So there's no interaction. So the only way you can actually get that to start working again and turning would be an active force that's in motion, dynamic, not the static force that's hidden or apparent normally in a magnet. But hidden within that static field is a dynamic magnetic wheel that is spinning 24 hours a day, and it's active. This is what I think it's doing. This whole area in here is going from that direction to this direction. So anywhere in there is a force that's lifting it up, as we saw with our magnets, the small magnets. What do I think is going on? How it's working? I think this neutral zone has a lot to do with it. We have a small wheel here. On this one, we are actually going clockwise. The larger one, on reference to this side here, we're going counterclockwise. So if you just get them right, you can have them add forces and work that way. If you get down too far, these wheels are going to hit like this. That's what this barriers are. This pulls back, and this one resists. So, but if you get out of there, get up out of that region, as you saw in the little experiments, you can see that go. Okay, this one was a little bit more inefficient. In the next bottle I'm going to bring out, I have 2 packs of 20s. Okay, let's go ahead and go to the next one. Okay, this is my other one. It's a little bit more efficient, works a little bit better, not as finicky. And again, VCR 12 volt. This system is completely isolated from this system, so anything that's doing the work is not because we're doing something to this system over here. It all has to do with this system. Okay? I'll go ahead and bring this back a little bit. It works on the same principle. These needles are very strong, watch your fingers. But this is going into the neutral zone, lifting up, getting out of there, back into the neutral zone, lifting with the magnetic wheel, and this is a small magnetic wheel. What I did different here, why it's more efficient, I put a little iron plate here that instead of having such a uniform field, now we're directing it. It's more concentrated because the field wants to go the least resistance. Instead of air, it wants to go with this iron, concentrates it, so we have a little bit better efficiency. I'm using 1 pack of Neos. See? There again, if you want to have it set so it's just spinning a little bit, it's okay. Okay, thank you so much for watching. Enjoy your inventing, research, development. Godspeed on it. Thank you much for watching.